Welcome dear learners. We are continuing quantum chemistry and in this module we are discussing some examples for first order perturbation. The contents of this module include an outline of the perturbation theory as a revision, non-degenerate perturbation theory, the helium atom problem a description, first order perturbation to normal helium atom, and as a second example, particle in only box with the slanted bottom. First of all, perturbation theory. Perturbation theory is an approximation method that describes a complex quantum system in terms of simpler system for which exact solution is known. That means perturbation theory give a solution to one problem in terms of already solved quantum mechanical system. Perturbation theory, as we know, categorized into two: time independent perturbation theory, which is proposed by Erwin Schrödinger, and time dependent perturbation theory suggested by Paul Dirac. Now, the word meaning perturbation, as you know, it is small disturbance. We are providing small disturbance to a system under consideration in its Hamiltonian. Perturbation theory consists of a set of successive corrections to an unperturbed problem, and the successive correction may be first order correction, second order correction, third order correction, and generally we are ignoring the contribution from higher order corrections and we are focusing up to second order correction, and this correction can be given to energy as well as wave function. In non-degenerate perturbation theory, there is no degeneracy of eigenstates is considered. However, in degenerate perturbation theory, we have to give the perturbation to degenerate eigenstates. In non-degenerate perturbation theory, perturbation treatments of degenerate systems and non-degenerate energy levels are quite different. That's why in non-degenerate perturbation theory, we are considering only non-degenerate eigenstates. If some of the energy levels of the unperturbed systems are degenerate, others may be non-degenerate. So, exclusively in non-degenerate perturbation theory, we shall consider perturbation on non-degenerate energy levels only. That means we are ignoring or we are avoiding the degenerate eigen levels or degenerate eigen functions. Now, we are trying to give the perturbation theory to the helium atom problem as an example. First of all, we have to give a brief introduction to the helium atom problem, and this is the description of the helium atom problem. As you are aware, the helium atom problem is a three particle system. What are the three particles present in the helium atom problem? The answer is simple. It consists of two electrons and a nucleus. Helium atom atomic number 2, so it has two electrons, and the two electrons are around the nucleus, and the nucleus consists of two protons. That's why the nuclear charge of helium atom is taken as +2 or +2 into E, where E is the unit charge of electron, that is taken as 1.602 into 10 raised to minus 19 coulomb. Therefore, the helium atom problem consists of three particles. One particle is the center portion, that is the nucleus, and nucleus is having a charge of +2 E. For atoms with atomic number Z, the nuclear charge is taken as +Z E, where Z is the atomic number. And in the case of the helium atom problem, we shall consider the nucleus, the helium nucleus with the charge +2 E is to be at rest and place the origin of the coordinate system at the center of the nucleus. That means, in the helium atom problem, the nucleus is at the origin and the coordinates begin at the center of the nucleus. The coordinates x, y and z begin from the center of the nucleus. That is taken for convenience. There are two electrons, as I already mentioned, and the electrons for convenience notated as 1 and 2. These electrons have coordinates x1, y1, z1 for the first electron and x2, y2, z2 for the second electron. And this is the pictorial representation. This we already studied whenever we have discussed the variation principle. and the helium atom problem. And in the helium atom problem, this is the center portion, that is the nucleus. The nucleus is having charge plus 2e. This is the second electron, this is being the first electron. And the distance of the first electron from the nucleus is taken as r1, and the distance from second electron to the nucleus is taken as r2. The inter-electronic distance is taken as r12, and everything is as usual. This is the notation for the helium atom problem. As I mentioned, r1 and r2 are the distance of the electrons 1 and 2 from the nucleus. r1, 2 is the distance from electron 1 and 2. Me is the electronic mass, that is simply 9.1 into 10 raised to minus 31 kilogram. This is the usual generalized representation of a helium atom problem, where we are going to apply the perturbation theory or the first order perturbation theory for correcting energy. Now, the Hamiltonian operator. This is the very popular Hamiltonian operator for the helium atom problem. Here also there are three important terms. The first term is minus s cross square by 2me del 1 square plus del 2 square. The second term being minus 2e square by 4 pi epsilon 0 into 1 by r1 plus 1 by r2. And the final term e square by 4 pi epsilon 0 into 1 by r12. Del 1 square del 2 square are the common Laplacian operator. We know about the Laplacian operator, that is dou square psi by dou square plus dou square psi by dou y square plus dou square psi by dou z square. Since we are having two electrons, we have two separate Laplacians remarked as lambda del 1 square and del 2 square, and these are Laplacians or Laplacian operator corresponds to electron first and electron second. Regarding various energy terms that appeared in this expression, we can have three portions in the RHS of the Hamiltonian operator. And the first term, as we mentioned earlier, the first term represents the kinetic energy part of the Hamiltonian, and the second term and the third term represents potential energy part, out of which the second term, which begins with a negative sign, indicates the potential energy of attraction. Attraction leads to low energy and hence stability. So, the second term is the energy corresponds to potential energy, and the potential energy arise due to attraction between oppositely charged bodies, namely the negatively charged electron and the positively charged nucleus. So, the second term that appeared in the Hamiltonian operator is as a result of the attractive force, the Coulombic attractive force between positively charged nucleus of charge plus Ze and negatively charged electron with the charge minus E. Finally, the last term E square by 4 pi epsilon 0 r 4 pi epsilon 0 into 1 by r undu is also a potential energy term, the coefficient of which is a positive sign, positive 1, or this positive value indicate that there is an increase in potential energy, and that term is taken as potential energy of interelectronic repulsion. Repulsion leads to high energy, so last term has a positive value, and we have to keep the fact that potential energy of interelectronic repulsion is the last term. So, first term represents kinetic energy, second term represents the potential energy of attraction, last term represents the potential energy arise due to interelectronic repulsion. This is about the Hamiltonian operator of the helium atom problem, and based on that Hamiltonian operator, we can set out a Schrodinger wave equation for the helium atom problem. The Schrodinger wave equation for the helium atom problem is in its complete form is like this. This we already studied in the previous modules, and for convenience I represent it once again. Minus s cross square by 2me del 1 square plus del 2 square psi r1 r2 minus 2e square by 4 pi epsilon 0 into 1 by r1 plus 1 by r2 psi r1 r2 plus e square by 4 pi epsilon 0 into modulus of r1 minus r2 psi r1 r2 is RHS equal to energy psi r1 r2. The Schrodinger equation, this Schrodinger equation mentioned here, this we already learned. This Schrodinger equation cannot be solved exactly for this system, and the inability to solve this Schrodinger equation is due to the existence of the last term. The existence of the last term. The last term on LHS. The last term on LHS arise due to interelectronic repulsion, or the last term having some parameter R onto parameter, R1 and R2. R onto parameter is occurring in the last term. That interelectronic repulsion parameter, interelectronic repulsion potential energy term offer hindrance to get correct solution to the Schrodinger wave equation. Therefore, we must resort to some approximation methods to solve the Schrodinger wave equation. That's why we are taking perturbation theory to solve this Schrodinger wave equation. Now, first order perturbation to normal helium atom. Thus, we just revised the concept of perturbation theory, first order correction to energy, the basic principle of the perturbation theory, and we discussed the initial part, or we give a complete description of the helium atom problem where we are going to apply the perturbation theory. And now we are giving first order perturbation to normal helium atom. The normal helium atom problem we have discussed just now itself, and we have to apply first order correction to the normal helium atom. It is possible to solve the Schrodinger wave equation for the ground state of helium using first order time independent perturbation theory. And let the Schrodinger wave equation to be solved for the helium atom is Hamiltonian psi is equal to energy into psi. I mark it as the basic equation and put it as equation number 1. And the Hamiltonian can be, for convenience, splitted into two parts. This concept we already studied, and this is decomposed into two parts, that is the total Hamiltonian splitted into two parts. The first part is unperturbed part and the second part is termed as the perturbation. H hat dash is termed as the perturbation. Actually, this equation must have a lambda term, that is perturbation parameter, and for convenience we are taking the perturbation parameter lambda is equal to 1 since we are discussing the first order perturbation. Therefore, H hat is equal to H hat 0 plus H hat dash, where H hat is the Hamiltonian of the present system described by Schrodinger equation 1, and H hat 0 is the unperturbed Hamiltonian, and the last part H hat dash is the perturbation. Where H hat 0 unperturbed part and H hat dash is the perturbation, and again lambda is taken as 1. So, it is not appeared in this expression. The unperturbed Hamiltonian H hat 0 is given by this expression, that is minus s cross square by 2 mu into del n square plus del 2 square plus z square minus z square by 4 pi epsilon 0 into 1 by r1 plus 1 by r2. You know the fact that Z is the atomic number. For helium, you can put Z is equal to 2, and epsilon 0 is the permittivity factor. Mu represents reduced mass of the helium atom. Del 1 square and del 2 square represents the Laplacian operator corresponds to electron first and second. The perturbation is the interelectronic repulsion term. I already mentioned that the inability to solve the Schrodinger equation to the present system arises due to interelectronic repulsion. Therefore, the interelectronic repulsion part is taken as the perturbation. That perturbation H hat dash is equal to E square divided by 4 pi epsilon 0 into R onto. R onto term appeared in the denominator. The R onto term, the existence of the R onto term offer hindrance to get exact solution. That is why the term involving R onto is changed into perturbation, and the perturbation part H hat dash equal to E square divided by 4 pi epsilon 0 R onto. This is the perturbation corresponds to the helium atom problem, and based on this perturbation we are applying the first order perturbation theory to the helium atom. Now, R1 and R2 you are aware, it is the distance of the electron first and second from the nucleus. R12 is the distance from electron 1 to 2. Zd represents the nuclear charge, and for helium the value of Z is equal to 2. In atomic units, that is the most convenient unit in quantum mechanics. In atomic units, it is always used for simplicity and for simple explanation. In atomic units, the Hamiltonian of the helium atom problem can be simplified and modified. That is, the Hamiltonian H hat 0 is equal to minus of del 1 square plus del 2 square minus 2 by R1 plus 2 by R2. Why put 2 is because of the fact that Z is equal to 2 and E is marked as unity since we are expressing this Hamiltonian in terms of atomic units. So, I got this simple relation. Moreover, the previous expression that corresponds to perturbation H hat dash diminished into this equation equation 4 diminished into H hat dash equal to 1 by R on 2. So, in atomic units, this is the Hamiltonian for the helium, and for the unperturbed part, or this is the unperturbed Hamiltonian, and this is the perturbation. Perturbation is H hat dash is equal to 1 by R on 2, and unperturbed Hamiltonian is minus half into del 1 square plus del 2 square minus 2 by R on plus 2 by R2. These two are important parts based on which we are shifting into the first order perturbation to the helium atom. Since H hat dash, that is perturbation, is very less when compared with the unperturbed Hamiltonian, it is pertinent to use the perturbation theory. Since H hat dash is the sum of two 1 electron Hamiltonians, the unperturbed wave function psi 0 can be written as the product of two hydrogen-like or hydrogenic wave functions. Thus, the unperturbed wave function psi 0 is marked as psi 0 R on 2 since it depends on R1 and R2. Psi 0 R on 2 is equal to psi 0 R1 into psi 0 R2, where psi 0 R1 and psi 0 R2 shown in equation 7 are two 1 electron hydrogen-like wave functions or hydrogenic wave functions. Here psi 0 Rj is the wave function of ith electron in a hydrogen atom with the nuclear charge Zd for hydrogen Z is equal to 1. Thus, psi 0 R on 2 is equal to Z cube by pi a cube the whole raised to 1 by 2 into e raised to minus Z R1 by A0, that is for the first electron, multiplied with Z cube by pi a cube, pi A0 cube the whole raised to 1 by 2 into e raised to minus Z R2 by A0. That is again equal to, this product again equal to, on simplification, the RHS will be reduced to Z cube by pi into e raised to minus Z into R1 plus R2. That is the expression, and remember that this expression, this simplified expression utilizes energy in atomic units, or this is in atomic units. Expression 8 is very important as far as the correction to the wave function as well as energy is concerned. The unperturbed ground state energy E0 is equal to sum of ground state energies of two hydrogenic atoms, two hydrogen-like atoms or two hydrogen atoms. So, E00 is equal to minus Z square by 2 plus minus Z square by 2, that is theoretically equal to minus Z square if we express this energy in atomic units. So, E00 is equal to minus Z square. To get to the first order corrected energy, we have to add first order correction with this value, this energy value minus Z square. Therefore, the first order correction to ground state energy, we already established this relation. E01 is equal to double integral psi 0 star R1 R2 H hat dash psi 0 R1 R2 D21 D22. This is represented in bracket representation like this. We have psi 0 R1 R2 equal to minus Z cube by pi into e raised to minus Z into R1 plus R2 in atomic units, and we have to incorporate equation 8 and equation 10 and to integrate and to evaluate the value of E01. The value of the first order correction to energy would be Z raised to 6 divided by pi square double integral e raised to minus 2 Z into R1 plus R2 into 1 by R1 R2 D21 D22, and this is a complex integration, and we know that D21 and D22 must be expressed in spherical polar coordinates, and D21 will be equal to R1 square sin theta 1 dr1 d theta 1 d phi 1, and D22 is equal to R2 square sin theta 2 dr2 d theta 2 into d phi 2. Therefore, we can put these two elements in equation 11 and we have to proceed with that complex integration. After the integration and the expression of the energy in atomic units, we get the final result as En E01, that is the first order correction to energy, will be equal to E01 equal to 5 by 8 into Z, 5 by 8 into Z. Thus, we already have this expression E00 is equal to minus Z square, and the first order correction to energy E01 equal to 5 by 8 Z. So, to get the energy of the system, we have to add this first order correction to E00, to the ground state energy, or the ground state energy of the system is equal to ground state energy of the unperturbed system plus first order correction. That means minus Z square plus 5 by 8 into Z. So, the value will be equal to E0 equal to minus of Z square minus 5 by 8 into Z. This energy is also in atomic units, and incorporating the original values, original unit, here instead of the atomic unit, we get E0 equal to minus of Z square minus 5 by 8 into Z into mu E square divided by 2 S cross square, where mu represents reduced mass of the system, S cross represents h by 2 pi, that is a constant known as Dirac. Thus, we got the energy of the system E0 equal to minus of Z square minus 5 by 8 Z into mu E square divided by 2 S cross square. Thus, we got the energy after first order correction equal to, or the total energy of the system equal to E0 equal to minus of Z square minus 5 by 8 Z in atomic unit. It should be noted that the ground state energy of hydrogen is minus half atomic unit. Minus half atomic unit equal to minus 13.6 electron volt. The energy of the hydrogen atom in the ground state is equal to minus 13.6 electron volt. That is theoretically equal to minus half atomic unit. Therefore, if I cancels the negative sign on both the sides, I will get half atomic unit equal to 13.6 electron volt, or 1 atomic unit equal to 2 into 13.6, that is 27.2 electron volt. We have the energy E0 equal to minus of Z square minus 5 by 8 Z into in atomic unit. So, instead of this atomic unit, I can put 27.2. Therefore, E0 equal to minus of Z square minus 5 by 8 Z into 27.2 electron volt. This part on simplification, by putting Z is equal to 2, since Z is equal to 2 for helium atom, I will get the energy after first order perturbation, the energy equal to minus 74.80 electron volt. This is the energy of the helium atom problem, normal helium atom, after giving first order perturbation to energy. That means minus 74.80 electron volt, that is again theoretically equal to minus 2.75 atomic unit. So, in order to get it in atomic unit, we have to divide it with the 27.2, since 1 atomic unit is equal to 27.2 electron volt. Therefore, minus 74.80 electron volt equal to minus 2.75 atomic unit. Thus, on applying first order perturbation correction to energy of the helium, we get energy of the system as minus 2.75 atomic unit. The experimental value for the energy of the helium will be equal to minus 2.904 atomic unit. That is same as minus 78.986 electron volt. The agreement between the theoretical and experimental value is not at all good, but that is recommended. If we are adopting second order and higher order contributions, then we will get better agreement between the calculated value and the theoretical value. Here we are applying only first order correction. That is why there is some difference between the calculated value and the experimental value. So, if we are adding more and more corrections, higher order corrections like second order, third order, etc., we will be in better agreement with the calculated value and the experimental value. Now, we are going to take another example for the perturbation theory, that is the system is particle in only box with a slanted bottom. This is a system where the particle is present in a gravitational well. So, this problem can be considered as a particle in a gravitational well, and here the bottom part is slanted. This is the description of the system. We can see two potential wells and the potential energy values are shown here, the conditions for the potential energy, and it should be noted that Vx is equal to infinity when x less than 0, that is x less than 0 means in the negative direction, and Vx is equal to infinity when x greater than a, because the edge length of the box is from 0 to a. This is where x less than 0, this position is where x greater than a. When x greater than a, potential energy will be infinity. When x less than 0, potential energy will also be infinity. That means outside the walls of this potential well, we can see the potential energy will be infinity. Then what about the situation inside the box? Inside the box, that is between 0 less than or equal to x less than or equal to a, or x lies between 0 to a, or inside the box, the potential energy can be calculated as Vx equal to V0 into x by a, V0 into x by a. That is potential energy not equal to 0 inside the box. But whenever we have discussed the particle in only box with a regular bottom, we took the assumption that potential energy of the particle inside the box is taken as 0 and the entire energy will be kinetic. But since the bottom portion is slanted, here we are taking the potential energy Vx equal to V0 into x by a and not taken as 0. So, potential energy inside the box is V0 into x by a. Outside the two walls, we can say Vx is equal to infinity. This clearly depicts the nature of the system, that is the particle in only box with the slanted bottom. Now, perturbation theory can be applied to particle in only box with the slanted bottom. This situation is simply termed as a gravitational well. This problem can be considered as a modified problem of particle in only box. That means the unperturbed problem is particle in only box. This simply implies that we can find solution to particle in only box with the slanted bottom by using particle in only box with the regular bottom as an unperturbed problem. So, we are correcting the particle in only box by applying perturbation theory to get the wave function and energy of particle in only box with the slanted bottom. Moving on to the corrections. The unperturbed problem is particle in only box. We already have the unperturbed wave function psi n0 x is equal to under root 2 by a sin n by a into x, where n is equal to 1, 2, 3, etc. This we learned with the particle in only box, and the energy of the particle in only box is given by En0 equal to n square h square by 8 mi square, where n is equal to 1, 2, 3, etc. So, these are the parameters for the wave function and energy for particle in only box. They are taken as unperturbed energy and wave function. The perturbation is to the potential, that is perturbation h hat dash is equal to the potential energy of the particle inside the box, that is V0 into x by a, and the limiting condition is 0 less than x less than a. or this potential exists between x is equal to 0 to a, x is equal to 0 to a. So, the perturbation parameter h hat dash equal to V0 into x by a, this is simply the potential energy of the particle inside the gravitational well. Now, the first order correction to energy to be evaluated. By using the same integral, we can evaluate the first order correction to energy. First order correction to energy En1 is equal to integral psi n0 star V0 x by a into psi n0 d tau. On substituting different values for wave function and on proceeding integration, we are getting the final value as En1 is equal to V0 by 2, where n is equal to 1, 2, 3, etc. N1 is equal to V0 by 2. The first order correction to energy is V0 by 2. Thus, the ground state energy of the particle in 1D box after first order correction will be E1 equal to E10 plus E11, where E10 is the unperturbed energy, that is energy of the particle in 1D box in ground state, plus E11, that is the first order correction, that we got as V0 by 2. We know for the ground state of particle in 1D box, the unperturbed energy will be h square by 8m square, because in the ground state n is equal to 1. And we have to add the first order correction, that is V0 by 2. Therefore, the ground state energy of the particle in 1D box with the slanted bottom after first order correction will be equal to E1 equal to h square by 8m square plus V0 by 2, where a is the edge length. The unperturbed energies and first order energies can be represented in the same diagram like this. This is the pictorial representation. In the pictorial representation, you can see that the solid lines represents first order energy and the unperturbed energy, that is the energy of the particle in 1D box, are shown in dashed line, and the first order energies are in above position of that of unperturbed energy. That means the particle in 1D box with the slanted bottom, that is the system under our consideration, has energy slightly higher than the unperturbed problem. So, this about the graphical representation of perturbed and unperturbed first order energies of the system. Thus, we have discussed the application of first order perturbation theory to the helium atom problem as an example, and we also exemplified the first order perturbation theory by taking energy correction to particle in 1D box problem with the slanted bottom. Have a nice learning experience. That's all about this module. Thank you.